Hi everyone, this is Janine the Tutor, your favorite math and science coach. Let's get better grades in less time, shall we? In this video, I will be covering naming acids, bases, and hydrates, so without further ado, let's begin. When we're naming acids, it's important to consider that there's two types of acids. We have non-oxy acids and oxyacids. So these two are categorized based on the presence of oxygen. So under non-oxy acids, so as the word implies, you don't have oxygen, you have hydrogen plus halogen. So halogens are found in group 7 of your periodic table. So if we're looking at HCl, we know that hydrogen carries a charge of +1, while chlorine carries a charge of -1. When you cross over their oxidation numbers, you end up with hydro plus the root, which is chloro in this case because it's chlorine, and then you have ic, which is your suffix for non-oxy acids, and you have acid, and as a result, it becomes hydrochloric acid. Whenever we're naming oxy acids, the huge difference between non-oxy versus oxy acids is dropping hydro in front of our name. So if we're looking at polyatomic ions that ends in ATE, for example, you have nitrate, in this case it's NO3-, you would have to cross over your oxidation number for hydrogen and nitrate, and as a result, you have to change your suffix into ic, so it becomes nitric acid. So as you can see, hydro is dropped from our name. Now moving on to polyatomic ions that ends in ITE. So for example, we have nitrite, which is NO2-. When you cross over the oxidation numbers of hydrogen and nitrite, you end up with HNO2. And as a result, you have to change the suffix into us, and it becomes nitrous acid. Now moving on to oxyanions and oxyacids. So whenever we're looking at oxyanions, in this case, we start with chlorate as an example. We know that it has 3 oxygen atoms and therefore it ends in ATE. Adding 1 oxygen atom to chlorate would give you perchlorate. So we simply have to add the prefix per. And going back to chlorate, when you have to reduce 1 oxygen atom from chlorate, you end up with chlorite. Reducing 1 more oxygen atom from chlorite, you end up with hypochlorite. And as a result, you still have to apply crossing over of oxidation numbers here. So for example, you have H plus and ClO4- when you cross over. As a result, you get HClO4. Because it's perchlorate, it ends in ATE. Therefore, it becomes ic as your suffix. So now it's perchloric acid. Now moving on to chloric acid, it's because it's chlorate to begin with as your polyatomic ion, and therefore when it becomes an acid, it becomes chloric acid. Now moving on to chlorite, because it ends in ITE as a polyatomic ion, it has to become chlorous acid, and if it's hypochlorite, it still carries the hypo, therefore it's hypochlorous because it's ITE to begin with, and you have OUS as your suffix. So it's hypochlorous acid. So to sum it up, if your polyatomic ion ends in ATE, your suffix when it becomes an acid is ic plus acid. And if your polyatomic ion ends in ITE, your suffix must become OUS if it becomes an acid. Now here's a chart that I made that are pretty common, which are monoatomic and polyatomic ions. So the only exception here is if you're looking at sulfate to begin with, sulfate has 4 oxygen atoms and it ends in ATE to begin with. Now it's very similar to the ones that I've talked about in a way that if you're adding 1 oxygen atom, for example, if it's now SO5-2-, you just simply have to add the prefix per. Now if you go back to sulfate, reducing 1 oxygen atom would turn it into sulfite. Reducing 1 more would become hyposulfite, and if you reduce 1 more oxygen atom, it becomes sulfite. So you have IDE as your suffix. Now when we're naming bases, there's only 3 ways to name bases. You have the strong bases, the common names, and bases that are based on their covalent bonds. So for strong bases, they're always going to be group 1 or group 2 plus the hydroxide ion, and you simply have to cross over their oxidation numbers. And the reason for that is because bases that are strong, that are group 1 or group 2 plus OH-, are considered Arrhenius bases, meaning Arrhenius bases are bases that can fully dissociate in water and increase the concentration of OH- in their surroundings. So therefore, you have K plus, meaning K is found in group 1 of your periodic table, carrying a charge of +1. You have the hydroxide ion, which carries a charge of -1. As a result of crossing over of your oxidation numbers, you end up with KOH as potassium hydroxide. Moving on to calcium hydroxide, we know that calcium carries a charge of +2 because it's found in group 2 of your periodic table. Now you have OH-, which carries a charge of -1. Therefore, when you cross over their oxidation numbers, you end up with calcium hydroxide. So common names, these are just names that you simply have to know by heart. So in this case, you have NH3 for ammonia, which is a base. And we also have bases that are based on their covalent bonds. So these are more the organic chemistry side because depending on their group, so for example, you know that this is methyl and this is an amine group. That's why it's called methylamine. And it's also a base. Now moving on to hydrates, we have anionic compounds and we have a prefix, which are an indicator of the number of water molecules that is present. So for example, if we're looking at CuSO4, 5H2O, we simply have to apply the rule for naming ionic compounds. And if you haven't watched that video, please do before watching this video. So if you're naming ionic compounds, going back to CuSO4, we know that copper carries a charge of +2. And we know that sulfate carries a charge of -2. When you cross over their oxidation numbers, you end up with Cu2, SO4, 2. However, you can cancel out the 2 and you end up with CuSO4, which is copper, 2 sulfate, because copper is multivalent. Now, for penta, because there's 5 molecules of water, and you just simply have to end this with hydrate. So when we're using the prefixes, this is very similar to molecular compounds in such a way that when we're using the prefixes, when we're naming molecular compounds, this is the same thing. So you have mono, di, tri, tetra, penta, hexa, hepta, and octa. And for 9, it's nona. For 10, it's deca. Now let's practice. So if we're looking at HF, we know that this is an acid, and this is a non-oxy acid. Therefore, the name has to be hydrofluoric. So the root is fluoro, and you have the suffix ic, and you have acid. Now for H2C2O4, you know that this is a polyatomic ion. C2O4 2- is actually oxalate. Therefore, when you cross over their oxidation numbers, you end up with H2C2O4. And this has to be oxalic acid. Now, moving on to sodium sulfate monohydrate, we see that this is a hydrate. We know that sodium sulfate is an ionic compound. Therefore, we know that sulfate has a charge of -2. Sodium has a charge of +1. When you cross over their oxidation numbers, you end up with Na2SO4 monohydrate. So that's simply H2O because mono indicates that it's one molecule of water. Moving on to phosphoric acid, because this acid ends in IC, therefore this must be phosphate. Because if your polyatomic ion, phosphate, ends in ATE, then if it becomes an acid, you would have the suffix IC. Therefore, this must be H3PO4. Because as a result of crossing over your oxidation numbers, you know that hydrogen must have a charge of +1, while PO4 must have a charge of 3- because it's phosphate. Now moving on to barium hydroxide, this is a strong base. In fact, you know that barium carries a charge of +2 since it's found in group 2 of your periodic table. Hydroxide carries a charge of -1. Therefore, this must be BaOH2. If you like this video, please don't forget to subscribe to the channel, hit the notification bell, and give me a thumbs up. Once again, this is Janine the Tutor, helping you reach your learning goals faster, and I'll see you on my next class. Bye, guys!